Okay, now we're ready to finish up with the last of the 6 problems. This one shown on the screen here is 11.3.16 OFN. We have a rigid tank that contains 3 kilograms of nitrogen at a given thermodynamic condition, connected to another rigid tank that contains 6 kilograms of oxygen at similar conditions, similar temperature, but at a higher pressure. The valve connecting the 2 tanks is opened. The 2 gases are allowed to mix, and we find that the final temperature is 25 degrees Celsius. We want to determine the final volume of each tank, or excuse me, the volume of each of the 2 tanks, and the final mixture pressure using the ideal gas model. And so a little bit different problem here. We know the mass and we know the thermodynamic conditions, and so we would know about the specific, we don't know the specific volume, but we would be able to determine the specific volume. And so we're going to then look to see what the volume of each of the tanks are, and then what the final mixture pressure is. Now, the volume in each of the tank is going to be determined from the mass and the thermodynamic properties. And so this mixing process is not going to have any bearing on what the volume is. The final volume, though, is going to dictate what the final mixture pressure is. And so again, we have a closed system. It is a mixing process. We are going to look at ideal gas for this binary mixture. And we'll then go to the test app. And now we're ready to assign the 2 gases. And in this case, it's nitrogen as the A fluid, and it's oxygen as the B fluid. And so once again, specifying the fluid A all as 1, we can put in a mass fraction of 1 for this particular state. We also know that there are 3 kilograms of mass. We also, in this particular problem, we know the pressure. The pressure was originally 250 for the oxygen, and we know that the temperature was 25. And so with this thermodynamic state, because we only needed 2 independent thermodynamic properties, that allowed us to calculate the specific volume. And since we had the specific volume in the mass, that allows us then to calculate the total volume. So the volume for the nitrogen side of this 2-tank system is 106. Okay, so now we're ready to go to the second tank, and the second tank is oxygen, and in our binary mixture, that means that there is no A, but it's all B. We know that the oxygen in that particular side is 2 kilograms. We also know that the temperature is given as 25 degrees. It's the same as what we saw before. And then finally, the pressure for that particular vessel is 450. And so once again, with the pressure and the temperature determined, that allows us to calculate the specific volume. It's an ideal gas. We know that PV is equal to RT. And so we then have the mass, this specific volume, and it tells us what the volume of that second tank is that originally starts with the only oxygen in it. And so now we're ready to go to state 3, and what we know about state 3 is that its temperature is equal to 25. And we also know that as it mixes together, that the final mass is equal to mass 1 plus mass 2. And so our final mass is 3 plus 2 are 5. We also know, due to volumetric constraints, that the final volume is equal to volume 1 plus volume 2. And so that final volume was going to be what we had before, 0.344 plus another 1.06. And so our final volume is given by that. So we have our final volume, we have our final mass. It can calculate the V3. And so this is a thermodynamic property. This is a thermodynamic property. And so with two independent thermodynamic properties, it then calculates what the final pressure must be, 295. And so in this particular case, the volume and the final mixture pressure have been determined. Okay, we don't really, in this particular case, we don't have to go to a process panel and designate this as state 1 and this is state 2 going to state 3 with no heat transfer and no work. It already calculates that. The only reason we'd want to go to this particular process panel is if they asked us something about the generation of entropy that occurs. And so what we are doing is we are going from one vessel that has only nitrogen in it and another vessel that only has oxygen in it, and we're now bringing those together into a third vessel. And what happens is each of the two fluids, each of the two substances feels like there is a lowering in its partial pressure, its fraction of what is there. And so that gives rise to a lowering in the change of entropy. And we see that as this SGen term. So once again, the answer to the problem of this particular problem is that the final pressure is 295, which makes sense because it's somewhere in between 250 and 450. And the final temperature, well, the final temperature, because of this equation right here, if there was no work and no heat transfer, the right-hand side was equal to 0. What do we know about the internal energy or the flow energy for an ideal gas? The flow energy is just a function of temperature. And so we basically are going from two masses that are at the same temperature. It's going to go to a final mass that's at that same temperature. So with that, that finishes up this particular problem.